Tonight we open a different map of the solar system, not the tidy classroom orrery, but the living one that breathes and drifts. The sun is a steady hearth. Around it, worlds keep time in slow, unequal steps. Between them lie clues the eye can miss, like faint handwriting only revealed when the page is held to the night. Some clues are sharp enough to catch the pulse. A thin traveller from another star once crossed our sky and brightened without a tail. It turned and glided on, leaving a small gravity and a larger question. Far beyond Neptune, a handful of distant orbits lean in the same direction, as if a quiet mass were arranging them from the dark. Beneath glassy ice, hidden seas may trade heat with rock and make chemistry sing in the quiet. And one pale giant rests almost on its side, turning as if sleep itself had set the axis. We will move through these mysteries one by one, slowly, without hurry. The aim is not to solve them here, but to hold their shapes clearly until the mind loosens, to let the unanswered become spacious and kind. The science is careful, the pace is soft, the path is meant for rest. Before we begin, let us gather our little midnight crew. If these voyages bring you ease, a gentle like or a simple subscription helps this calm reach others still awake. Tell me the hour you are drifting tonight in the comments, whether that may be midnight, 2 a.m, or even dawn's edge, so I can chart our resting constellation and time future journeys to meet your night. And if you want to sink deeper, the Midnight Voyager playlist is waiting. Now, allow yourself to settle. Let the breath fall in and out, unforced. We are going mystery by mystery now, one clear facet at a time, letting each cool the mind and widen the room. When you are ready, we begin a quiet voyage through unsolved cosmic mysteries, questions that feel impossible and somehow make rest easier to find. Tonight we begin with a passage and a question, a brief crossing that left the sky a little different. Imagine a slender thing, sunlit and quiet, arriving from far beyond the outer dark, skimming through our neighbourhood and vanishing again into the deep. It moved as if the solar system were a room with the door slightly open. It stepped in, looked once and slipped back out. Astronomers first saw it in 2017. Small against the noise, a moving point among points. It traced a path that was not a loop. Its orbit was open, hyperbolic, the clear signature of something born under another sun. In Hawaiian, it was given a name that means scout, a messenger that comes first. The name fit, and it still does, because what we learned was not final. It was the beginning of a longer conversation about what drifts between the stars. What we could measure was brief, yet it carried texture. As the object turned, its brightness rose and fell like breath. The light curve suggested an unusual shape, perhaps long and thin, perhaps wide and flat, certainly not the neat pebble we might imagine. There was no glowing veil of gas and dust, no familiar streamer that tells of a warming comet. It brightened with sunlight, it tumbled, it kept its silence. Then came the smallest surprise, so quiet it might have been missed. The path of the object did not follow gravity alone. There was a faint, additional push. Sunlight can do this, pressing on surfaces the way a tide presses on a shoreline. So can gases that evaporate invisibly from heated ice. The numbers were delicate, the effect subtle, but the inference was clear enough to consider. Either the visitor was shedding something that left no bright trace, or it was so light for its size that radiation itself could nudge it. These are the kinds of forks where science takes a thoughtful pause. One path imagines exotic ices, the kind that turn directly to vapour and sunlight without producing a dusty halo that a telescope could easily detect. Hydrogen ice or nitrogen ice or a carbon-bearing frost could, in principle, whisper away into space, providing a steady, gentle thrust. Another path imagines a body with the density of folded snow, a porous aggregate so airy that sunlight's pressure matters, or a naturally thin shard, a wide plate formed by processes we have not watched up close. The ideas are careful, not sensational. Each tries to hold every clue at once and see if the picture holds. We did not see the surface directly. We watched light and motion and pulled meaning from their changes. The colour was slightly reddened, like many ancient surfaces baked by cosmic rays in the cold. The rotation was not simple. It seemed to tumble rather than spin neatly, a sign of past jostling or a shape that resists balance. The object was small on human scales, yet not a speck, large enough to be a world in miniature, small enough to escape direct detail. With each observation, the mind drew a more specific silhouette, and with each silhouette came new questions. There is a feeling that arrives when evidence is thin and the stakes are gentle. It is not frustration, it is an easing, a recognition that the world will keep some room for wonder. We caught a single page torn from a book that continued out of sight. The letters were legible, the context was not. Later visitors will bring more pages, perhaps even chapters, and then the shape of the story will become clear. For now, we hold the page we have and read it slowly. The most soothing truth we can offer here is also the most honest. Nothing about this visitor required anything supernatural. Nothing demanded an answer outside the long library of nature. The hypotheses are plain and patient. Unusual ices, fragile aggregates, fragments shed from larger bodies in other systems where collisions and freezes happen under different rules of light and distance. It is the ordinariness of the proposals that feels beautiful. The universe can make many things, and sometimes we meet them only briefly. At the same time, there is music in the unknown. Between stars, there are highways of small bodies that we have not mapped, lanes of dust and ice and stone that drift for millions of years until a path and a gravity well align. Most of that traffic goes unseen. Now and then one crosses the glow of our instruments, and for a few weeks we listen. We listen with telescopes on mountaintops, with software that tracks tiny motions across a busy sky, with quiet math that extracts orbits from dots. Each detection widens the room a little more. Think of the solar system as a village at the edge of a long river. We know the houses, the footpaths, the groves where the wind combs the trees. What we do not often see are the boats that come from far away, thin and low in the water, passing in the night. When one does, the villagers step outside and watch the lanternless hull go by, hearing only the soft noise of the current against wood. In the morning they talk about it, and someone records the time and the river height and which way the reeds leaned. The river itself is unchanged, yet the village knows it better. How does this help us rest? It gives the mind a clear shape to hold, a story that is complete enough to dwell in but open enough to be gentle. A thing came, it turned in the light, it felt more than gravity. It left. Natural explanations wait, each with images attached that do not crowd the senses. A thin sheet warmed by the sun, a snowflake of stone and void pushed by light, a shard of distant ice making its quiet steam. You can place any of these in the dark behind your eyes and watch it move without hurry. There will be more. Our surveys are sharper now. Our instruments learn to scan wider fields and gather fainter motions. Each new interstellar object will carry its own set of clues, its angle of sunlight and its pattern of spin. Some will wear obvious combers and long tails. Some will stay austere and tight. In time, the unusual will feel familiar, and the first scout will seem less alone. We will have a small taxonomy of travellers from other suns, and the solar system will feel less like an island and more like a harbour. For tonight, we keep only what we need. A messenger came from afar and taught us that the space between stars is not empty. It is seeded with possibilities, with solids that carry histories in their shapes. We learn that gravity tells most of the story, but not always all of it. That light itself can push. That the absence of a glow can be as instructive as its presence. We learn that the patient act of watching is already an answer of sorts. The visitor leaves us with a clean, quiet truth. Space between stars is not empty, and sunlight can push as surely as gravity can pull. The simplest possibilities fit the clues. fragile aggregates, unusual ices, a shard from a distant system, and they are enough. We close the observation log, but not the question. Its wake points outward like an arrow drawn in faint light. Beyond Neptune, the handwriting of gravity stretches long. Distant orbits tilt, as if something slow and cold is nearby. If a hidden mass shapes that pattern, its presence will be felt before it is seen. Keep the calm you found. We turn the page to the far rim, where the sky is sparse and the clues are delicate, and we read for the quiet pull that may reveal a world we have not yet met. There is a quiet place beyond Neptune, where sunlight thins and years grow long, a country of slow ellipses and deep cold. We call it the Kuiper Belt, but the name makes it sound like a neat ring. It is not neat. It is a scatter of worlds and fragments, each keeping its own appointment with the sun, each carrying hints about how our system came to be. In that far hush, some orbits tilt and cluster in a way that feels deliberate, as if a hand we cannot see were tidying the chessboard. The proposal is simple to state and hard to prove. Perhaps a massive unseen planet circles far outside the known eight, slow and dim, shepherding those distant bodies into patterns. If such a planet exists, it would be cold as shadow and heavy as a handful of Earths, moving on an orbit so wide that a single year on that world could span millennia of ours. It would be no rebel tearing at the system, rather a steady influence that leaves fingerprints on the orbits of small icy worlds we can see. The fingerprints are subtle. A handful of distant objects appear to point their long axes in roughly the same direction, and many share a similar tilt with respect to the plane where most planets travel. Ordinarily, we would expect random spread. Gravity and time like to mix things. Instead, there is a lean, a shared hush, as if some unseen metronome were keeping time in the dark. But the outer solar system is as tricky to read as handwriting in low light. We do not survey the whole sky all at once. We look where our telescopes are pointed, under the weather we are given, at the times we can. Distant bodies are clearest when they are closest to the sun and brightest, which means we tend to find them in certain parts of their orbits. Bias creeps in like dew. Patterns can emerge not from nature, but from the shape of our search. This is why the question remains open. Some careful surveys designed to measure their own blind spots find less clustering than first reported. Others argue that even after accounting for those limits, the lean remains, a real effect, not an illusion. The debate is not loud, it is a conversation at a chalkboard, terms defined, uncertainties admitted, numbers crossed and rewritten until they agree. In the meantime, the sky keeps its counsel. Suppose for a moment that the shepherd is real. What could have placed it so far away? A planet a few Earth masses in size is not easily kicked to the edge and left there. Models imagine early times when the giant planets were still wandering, scattering small bodies like chaff. A massive core could have been flung outward and then, over ages, its orbit tamed by the gentle drag of countless, icy fragments, until it settled into a wide, cold path. Other stories picture a capture from the birth cluster of the sun, a stray child adopted in the crowded nursery where stars are made. Each version is a precise possibility, not a fantasy. The outer dark has room for many slow histories. Now suppose the shepherd is not there at all. Could the pattern arise another way? Many small bodies acting together have gravity of their own. A heavy extended disk can shape orbits without a single ruler. The galaxy itself pulls, a faint tide that lifts and lowers the far edges of our system over eons. Some propose that a long ago passing star tugs the outer region into a strange order that persists, and always bias hums in the background. A reminder that the more carefully we count, the more the picture can change. What would decide the question? A direct sighting would be decisive. A distant planet this faint would not sparkle. It would be a coal in the ashes, dark invisible light, gently glowing in the infrared. Wide field cameras comb the sky. Surveys map patch after patch, building a mosaic of motion. The candidate would move slowly, a pinprick shifting against the fixed stars over weeks and months. It could be hiding low to the horizon from our best observatories, or in a crowded field, or in the slice of sky we have not yet swept deep enough. Short of a clear image, the shepherd can still leave tracks. The lean of distant orbits could sharpen as we discover more of them, their apses aligning like needles with a hidden magnet. The inclinations could show a particular spread that math predicts only in the presence of a far mass. Detached objects, worlds whose closest approach to the Sun is too distant for Neptune to have shaped, could pile up in a way that demands an invisible partner. Each new discovery adds a grain of weight to one side of the scale or the other. There is a gentleness to this kind of mystery. Nothing is urgent, nothing is in danger. We are deciding between arrangements of ice under faint light. The stakes are only knowledge and wonder, and the way we understand our neighbourhood. Yet even gentle questions can help the mind settle. They give it a shape to hold, an outer stage where a slow actor may or may not be walking, the extras reacting in patterns that either signal a presence or do not. Some names have become touchstones in this story. Sedna, whose closest swing toward the Sun is so far that Neptune cannot be its sculptor. Other distant bodies with drawn-out ellipses and matched tilts. Their paths are notes in a melody. We hear a phrase and ask whether there is an instrument we have yet to see. The score is incomplete, but not chaotic. We keep listening. If the shepherd is found, it will not be a monster or a miracle. It will be another world, bound by the same laws, telling us that planet-making can scatter pieces much farther than we used to think, and that what seems empty is often occupied by something slow. If the shepherd is not found, we will have learned something just as valuable, that many small masses can arrange themselves into an order that looks like a single hand, and that our surveys must be even more careful than before. Either way, the edge becomes clearer. There is also a quiet art in how we search. Astronomers subtract starlight, stack images, follow faint shifts across seasons. Software watches for motion where the eye would miss it. Instruments are tuned to warmth rather than shine. It is patient work. It suits the subject. The hypothetical planet moves so slowly that it asks us to match its pace to meet it. Let this chapter close with a steady thought. The outer system is not a barren moat. It is a living archive. Whether a hidden planet writes in the margins or not, the text is there, waiting to be read with better light and better order. The mind rests well when it knows the difference between absence and uncertainty. Here the uncertainty is honest, and the absence is not yet proved. Next we turn inward, not to the heat of the inner planets, but to cold shells that hide warmer seas. Under ice that gleams with starlight, energy and chemistry meet in the dark. We will listen there for a different kind of possibility, one that stirs more quietly than gravity and is just as real. There is a strange comfort in thinking of oceans where sunlight never reaches. Not surface seas that flash and storm, but hushed waters sealed under ice, warmed by the slow press of tides and the heat of stone. In the outer system, several worlds carry that quiet possibility inside them, and the evidence is not a rumour. It is careful, accumulating, and patient. Start with Europa. Its skin is ice carved into double ridges and broken into rafts that look as if a frozen crust drifted and refroze. Beneath, scientists think there is a global ocean. The hint came first from magnetism. When Jupiter's field sweeps past, Europa responds as if a conducting layer lies within, a sign of salty water that can carry currents. The surface salts look altered by radiation, their chemistry changed by the giant planet's energetic breath. Cracks could trade those oxidants downward, where they would meet a darker world rich in reduced minerals. Together they make a gradient, a gentle battery life might use. Enceladus tells the story in a different way. At its south pole, long fractures open and breathe. Plumes of vapour and ice rise into space. A spacecraft sampled the spray and found salts, organic molecules, and hydrogen free in the mix. That hydrogen is important. On Earth, seafloor vents form when water meets hot rock and is split, releasing hydrogen that microbes can eat. The grains in Enceladus's plume include tiny bits of silica that look as though they formed where warm water touched rock at temperatures high enough to matter. The moon is small, yet its interior seems busy. The ocean there may not be deep, but it is active, and it is connected to a rocky floor. Ganymede and Callisto carry subtler signs. They're larger and colder. One has its own magnetic field, unique among moons, and both behave as though layered with stacks of ice and water, pressed by gravity into phases unfamiliar on Earth. Their oceans may be sandwiched between ice above and ice below, with salt and pressure shaping the chemistry. The interest here is not drama, it is time. Thick shells and steady interiors could hold conditions for very long spans. Even Pluto, far beyond the main stage, offers hints of interior softness. Its heart-shaped plane shows convection patterns, as if nitrogen ice flows over a heat leak from below. The entire dwarf planet seems to have reoriented in the past, as if a subsurface sea shifted weight and turned the shell. The case is not closed, but it is compelling. An ocean can be old and still influence a world's posture. Oceans need energy and chemistry, not sunlight. Tidal heating flexes a body as it orbits near a giant. The kneading warms ice and rock from within. Radiogenic elements decay slowly and add their quiet heat. Where water meets stone, reactions split molecules and set up redox differences that living cells, if present, could use. On Europa, oxidants made at the surface by radiation might travel down. On Enceladus, hydrogen rising from rock could meet oxidized sulfur from the ice. These are ingredients, not proofs. They say only that the pantry is stocked. The unsettled parts are the ones that keep the mind gently engaged. How thick is Europa's ice? Thick enough to keep the ocean safe, or thin enough for occasional cracks to reach through? How often do the tides make fissures that connect surface and sea? Are there long-lived vents on the seafloor, or only brief episodes after quakes? What is the pH, the salinity, the inventory of trace metals? Each answer changes the kind of life that could be comfortable there, from cells that eat hydrogen to those that rely on oxidants delivered from above. Titan is its own kind of riddle. On the surface, it is colder than any ocean we know. Lakes and rivers of methane and ethane play the part water plays here, cycling with weather and seasons. Beneath, gravity mapping suggests a deep ocean of water mixed with ammonia, a mixture that stays liquid at lower temperatures. The chemistry is gentler there. Ammonia lowers the freezing point and changes the dance of ions. Life as we know it would have to be patient. Life not as we know it would find a different kind of room. The question is not one of fantasy, it is one of chemistry and time. How would we tell if anything stirs in these seas? The most peaceful answer is to let the worlds tell us in what they already release. When a plume rises, a mass spectrometer can weigh molecules, looking for patterns hard to make without biology. Certain chains with consistent lengths, particular ratios of isotopes, a bias in the handedness of molecules that on Earth life strongly prefers. A single measurement is not enough. Nature knows many paths to similar products, but a suite of clues all pointing gently in the same direction can make a strong case. Even without plumes, surfaces can hold whispers. Cracks lined with certain salts could signal ocean water, reaching high and freezing in place. Heat patterns might trace conduits from below. A slight wobble in a moon's rotation can reveal a decoupled shell, ice moving over liquid. Each observation is a small note. Together, they build a theme. There is a reason the idea of hidden oceans feels so restful. It shows a cosmos that keeps quiet rooms, places where energy, water and time meet without spectacle. It shifts the centre of habitability, away from the harshness of distance from the sun, and toward the softness of interior processes. Worlds do not have to stand in the inner circle to be alive with chemistry. They only need a way to keep water liquid and gradients steady. The unknowns remain, and they are not loud. We do not yet have a map of a seafloor under ice beyond Earth. We do not know whether oxidants reach the depths in amounts that matter, or whether vents persist long enough to build communities. We do not know whether cells could move in these oceans, or cling to rock near vents, or remain sparse and slow, leaving only faint signatures in the water. Each we do not know is an invitation rather than a wall. What we do have is a path, instruments that sniff for complex organics and measure their shapes, magnetometers that feel the tug of conducting layers, cameras that read the grammar of cracks and braids on ice, altimeters that sense the rise and fall of a shell over tides. Missions will pass in wide loops, taking repeated readings. Some may sample plumes again, searching for chemical imbalances that are difficult to maintain without continuous sources. No single result will be treated as a drumbeat. It will be a chord, assembled piece by piece. Hold a simple picture, a dark ocean turning under a roof of ice, warm where rock meets water, quiet where salt settles out and falls like slow snow. It is not a promise, it is a possibility, refined by measurements and tempered by patience. That is enough to sleep on. Let the thought close gently around a steady line of truth. The outer system does not end in stillness. It shelters motion, an exchange hidden from the eye. If life is only comfortable on worlds that keep liquid water, then the solar system offers more rooms than we once imagined, and they are lit from within. We will keep the calm and change the angle. Next, we step back to a pale giant that lies nearly on its side, its seasons wrapped around its equator, like long ribbons. The mystery there is not water, but memory. What could have turned a planet and left it resting so quietly, ringed and reserved, as if the tilt were part of its nature from the start? There is a world in the outer system that keeps its equator, where most planets keep their poles. Uranus turns with its axis laid almost in the plane of its orbit, a slow roll rather than an upright spin. For long seasons, a pole faces the sun, and the other faces space, daylight and night stretching into decades. Rings and moons follow that tilted plane like a fallen hoop, circling a planet that seems to be quietly reclining. The tilt is not a small quirk. It is nearly a right angle, about 98 degrees. In most planetary systems, we expect modest inclinations, gentle nods to the forces that shaped them. Uranus looks like an exception written in large, careful letters. The question that follows is simple and difficult in equal measure. What could turn a planet so far and keep it there for billions of years? The first idea remains the most intuitive. In the crowded youth of the solar system, protoplanets collided. A single glancing blow by a body, a few times the mass of Earth, could have rolled Uranus onto its side. The moons and rings would then form from debris in the new equatorial plane, and the planet would cool into quiet. This picture fits the tilt and the orientation of the rings. It explains why the whole Uranian system shares that sideways geometry. Yet every simple picture earns questions. A giant impact should leave a heat signature in the interior for a long time, a kind of thermal memory that slowly fades. Uranus today radiates little internal heat compared with Neptune, its near twin in size and composition. That coolness can be folded into the impact story if the collision created stratified layers that trap heat and prevent it from flowing outward efficiently. But it is not a proof. It is one thread among several. A second path imagines many smaller encounters rather than one great event. Repeated glancing blows could aggregate into the same result without the violence of a single strike. The moons might still settle into the tilted plane. The rings could be leftovers of later collisions among captured debris. This version tends to be gentler on the planet's internal structure, though it demands a busier early history. There is also a slower mechanism that does not need impacts at all. A planet can be tilted by the steady pull of gravity if its spin axis and orbital plane drift into a particular kind of resonance. Imagine Uranus with a very massive moon in its youth, or with a thick disk of material orbiting around it as the moons were forming. The gravity of that companion or disk can torque the planet's equator. Over many millions of years, the torque can push the spin axis into a high obliquity state. If the massive moon is later lost to tidal evolution or ejected by interactions, the planet can remain tilted. The resonance no longer active, but the result preserved. These ideas can be tested indirectly by looking at the present system. The main moons of Uranus are regular and aligned, as if they grew in a disk after the tilt was already in place. Their surfaces show signs of old activity, but not the kind of recent extreme heating that would be required by ongoing dramatic changes. The rings are narrow and dark, shepherded by small moons, a restrained system compared with Saturn's luminous bands. The magnetic field is tipped and offset from the centre, an indication that the internal flows generating it are arranged unlike those inside Jupiter and Saturn. Each clue sketches a little more of the planet's inner character. The contrast with Neptune is part of the mystery. Neptune is similar in mass and radius, likely similar in composition, yet it emits more internal heat. It also spins with a modest tilt. If a giant impact sculpted Uranus, then the pair may have diverged because one suffered a major event, while the other did not. If resonant tilting did the work, then perhaps Neptune avoided the specific conditions needed to climb into a high obliquity state. Side by side, the two ice giants become a quiet experiment in planetary history. What would decide among these stories? A dedicated orbiter could weigh the planets with enough precision to reveal how mass is layered inside. Gravity measurements map interior density in broad strokes. The deeper the instruments can trace subtle variations, the more sharply they can outline any stratified shells left by a past upheaval. Magnetometers can read the geometry of the dynamo, showing where conductive fluids flow and how they are arranged. Long looks at the rings and the small inner moons can reveal collisional histories that speak to how the system settled. Even from afar, there are gentle strategies. Stellar occultations, when rings or a moon pass in front of a distant star, can refine shapes and densities. Thermal observations across seasons can show how the atmosphere stores and releases heat, a clue to what lies beneath. Models can test whether a massive lost moon could have tilted the planet without tearing the system apart, and whether today's moons could be the remnants of that process. None of this requires anything outside the ordinary library of nature. Worlds are shaped by collisions, by tides, by slow exchanges of angular momentum. A high tilt is surprising because it is rare, not because it is impossible. Uranus sits at the edge of our expectations and asks us to broaden them slightly. There is a quiet poetry to its present life. For years at a time, a pole faces the sun, and the other is wrapped in night. The upper atmosphere responds with faint bands and storms that come and go with the light. The rings cast thin shadows across the haze, then vanish when seen face on. Moons orbit in a plane that sometimes looks like a stacked set of coins and sometimes like a thin line. The planet does not advertise its history. It keeps the results and lets the cause remain a problem to solve. Why does this help the mind settle? Because the possibilities are concrete and calm. A singular ancient strike, a slow gravitational dance with a heavy companion now gone. A layered interior that holds its heat like a blanket. Each image is specific without being noisy. Each carries a sense that time is long and nature is patient. There is also a soft invitation to humility. We have flown past Uranus only once, with a brief encounter that sketched more questions than answers. From those few days of direct seeing, plus careful work from telescopes, we have built a set of stories that fit what we know and leave room for what we do not. The next close mission will not only refine the picture, it will likely change which questions feel most important. Uranus stays behind like a quiet mark in the record, its posture an archive that does not fade. The angle to the sun, the hush of its interior, the way rings and moons keep that sideways plane. Each is a line in a journal written by gravity and time. Reading it well asks for patience. Patience is the rhythm we keep. Inward, another riddle glows. A bright world veils itself in cloud and heat, its ground hidden, its history argued in careful tones. Traces of fresh volcanism, hints of long-ago water, evidence of a surface remade and remade again. The clues point both to tenderness and to furnace. We move toward Venus now, listening for which story it will allow us to hold. There is a bright world that keeps its face turned in slow motion, wrapped in cloud and heat, reflecting sunlight with the softness of ivory. From far away, Venus looks serene. Up close, it is anything but. The air is dense and heavy. The ground glows with stored warmth, and the clouds are not water at all, but droplets of acid, riding winds that circle the planet in a few days. The surface takes months to spin once. The sky above races. The mystery begins with a simple fork. Was Venus ever gentle? Long ago, could it have worn shallow oceans and a cooler sky, only to drift into a runaway greenhouse that boiled its water away? Or did it start hot, stay hot, and never pass through a blue chapter at all? Both paths are consistent with what we see. Both explain different parts of the record. The truth may not sit entirely with one or the other, but somewhere in the space between. What we know is plain. Carbon dioxide fills most of the air. Thick clouds hide the surface from visible light. Beneath that cover, heat is trapped the way a quilt traps body warmth, but on a planetary scale. The ground pressure is crushing, and rocks glow in the infrared like coals banked for the night. The clouds themselves are cold aloft, bright and high, and yet they make the world below hotter by holding in radiation that would otherwise leak away. There are hints that water once visited in greater measure. Venus's atmosphere holds more deuterium relative to hydrogen than Earth's. It is a clue that light hydrogen escaped to space more easily over time, leaving behind a fraction that is heavier. It does not prove oceans. It does say that water, however delivered, however stored, was processed and lost. The scale of that loss is the letter we cannot fully read. The ground seen by radar does not tell a simple age. Much of the surface looks young on geological timescales, with relatively few impact craters. Some terrains, called tesserae, are folded and crumpled like old paper, perhaps older than their surroundings, perhaps a memory of a time before the current face set. The absence of many very old craters suggests that Venus was resurfaced by widespread volcanism, or by a global overturn of the crust, or by episodes that erased the oldest pages. How often that happened, and how recently, are questions the planet keeps beneath its veil. Heat tries to rise from the interior. On Earth, it vents through plate tectonics. Thin moving plates carry seafloor away from ridges, dive at trenches, and recycle rock. On Venus, the ground seems more like a single lid, thick, strong, and mostly immobile. A stagnant lid can still breathe, just differently. Heat builds until it finds release through broad volcanic rises, coronae like collapsed domes, and rifted belts where the crust stretches. Some features look fresh, their edges sharp, their flows unsoftened by time. Recent studies of old radar images found changes at a volcanic vent that suggest activity in the human era. If lava is still moving in places, the planet's furnace is on a low simmer. Above, the clouds carry their own puzzle. The winds at those heights circle the planet in a few days, far faster than the ground turns. An atmospheric super-rotation driven by sunlight and waves. Particles in the clouds absorb and reflect in a way that is not fully matched by standard chemistry. There is talk of unknown absorbers, likely mineral or molecular, that darken specific bands of light. Sulfur cycles through the air as gas and droplets. Lightning may crackle in the clouds, though the evidence is mixed. The air is a machine of moving parts, some of which we can name, some we can only infer. From time to time, a more delicate claim stirs the conversation. A faint signal in the spectrum, a suggested molecule that on Earth would be unusual in air without a source. Interpretations come and go as methods are refined, as instruments are recalibrated, as other teams look again. The tone is properly careful. In a place this harsh, with photochemistry this active, patience is the only good tool. If there is a surprise hidden in the clouds, it will endure scrutiny. If not, the scrutiny will teach us better ways to read. Even the spin is an enigma with a calm face. Venus rotates slowly and backwards compared with most planets. Tides in its thick atmosphere, torques from the sun, and the shape of the solid planet can together settle into such a state over long spans. The slow day means long, lingering mornings and evenings in the clouds. Light filtered through kilometres of haze, temperatures changing not by hour, but by season of the planet's long solar day. It is a reminder that climate is not only about distance from the sun, but about how a world stores and moves heat. The unsettled questions keep their edges soft. If Venus once wore oceans, how long did they last before sunlight and air stripped them away? If it never did, how did the crust and atmosphere arrive at this locked partnership, with heat bottled and land remade in broad strokes? Are the tesserae ancient highlands left from a more mobile time, or simply thickened lids within a single style of tectonics? How often does lava make new ground, and where does that heat go once it arrives? Each answer does not shout, it adds a note to a chord. Why does this help us rest? Because the uncertainties are framed, not loose. Every proposal is a physical picture you can hold. A planet with a lid that lifts at the edges, a sky that runs faster than the ground, a surface that has been ironed smooth and then wrinkled again. None requires fantasy. All are ordinary in the library of possible worlds. Venus is not a cautionary tale shouted across the void. It is a study in how planets choose different balances between heat, air, and stone. The way forward is likewise steady. New missions will weigh the air more precisely, smell the chemistry of the deep clouds, and look through them with radar sharp enough to see small changes over time. Descent probes will taste layers as they fall. Orbiters will map cracks and domes and slopes that hint at what lies underneath. With each pass, the world we imagine will be corrected toward the world that is. Venus lingers as a study in balances. Heat stored and released, air in motion over rock that remembers being remade. Its story is not a warning shouted across space, but a quiet ledger kept in pressure, chemistry, and shape, waiting for patient readers to turn the page with better tools. Ahead lies a gentler riddle. On Mars, a faint breath comes and goes, appearing in small surges, then thinning to almost nothing. Stones, sunlight, and hidden pores may explain it. Something living in the deep past or the present would whisper the same way. We'll follow that flicker next, listening without hurry. The Martian air is thin, cold, and old, yet from time to time it seems to quicken. Instruments near the ground have tasted a trace of methane that rises and fades, a faint presence measured in parts per billion. Too small to see, yet large enough to notice. Overhead, orbiters have searched the same sky and found almost nothing, setting up limits that press the signal towards silence. Between the near whisper and the blank report lies a puzzle that is gentle, persistent, and very much alive. Methane on a sunlit world does not last. Ultraviolet light and reactive fragments in the air break it apart on timescales short enough that any gas we do detect must be recent. That one fact keeps the door open. If methane sits over a landscape and we still find a trace, then the planet is making it now, or releasing it from somewhere it has been stored. The options are ordinary in the library of geology and chemistry. The difficulty is choosing among them with care. Close to the ground, a rover's laser spectrometer has logged tiny spurts, even a seasonal rhythm, as if the gas swells when air is warmest and drains away when the cold returns. The pattern is not smooth. It behaves like a breathing system with multiple valves. Meanwhile, a spacecraft that peers through long slices of atmosphere at sunrise and sunset finds almost nothing, as though the column above the rover is clean. This tension is not an error in temperament, it is a difference in vantage. Near-surface air can be layered by time of day and wind. trapping a trace that dilutes to invisibility a few hundred meters up. A fleeting plume can be local, transient, and still entirely real. If geology is speaking, its grammar is known. Deep in fractured rock, water can meet iron-rich minerals and split apart, releasing hydrogen that reacts with carbon to form methane. On Earth, we call part of this suite serpentinization. Heat from ancient volcanism can bake leftover carbon-bearing materials. Tiny impacts can crack fresh surfaces and liberate gases from cages of ice called clathrates, where molecules were stored under pressure in the past. Even dust, salts and sunlight can play small roles at the surface, nudging chemical reactions forward when the air is still. If biology is speaking, its voice would be soft and meticulous. On Earth, microbes that feed on hydrogen, in the presence of carbon dioxide, make methane as a byproduct. They thrive in places without light, near chemical gradients that can power their metabolism. Mars has rocks, pores and ice. It has slow trickles of oxidants from the surface that could meet reduced minerals below. It has a climate that once allowed rivers and lakes. The thought does not promise. It only says that the setting is familiar to life as we know it. If cells ever took hold there, present or past, methane would be one of the gentlest ways they could declare themselves. Destruction has its own strong case. The Martian regolith is seasoned by radiation and dust storms. It hosts oxidizing compounds that can consume methane quickly near the surface. Sunlight makes radicals that tear molecules apart. The winds stir boundary layers that carry traces into air where they are swiftly erased. In such a world, one instrument can taste a flicker before dawn, while another, looking through the full height of the atmosphere, records none. The physics does not argue. It asks us to be more specific about place and time. Numbers are not the only guides here. Texture matters. Are the bursts sharp or smooth, tied to certain hours or winds? Do they cluster near particular rocks or slopes? Does the signal rise when pressure falls, as air draws gas from pores, and sink when pressure climbs? A pattern can betray a mechanism, even when the absolute amount stays stubbornly small. Repetition, more than grandeur, is what the planet owes us. Instruments are learning to match the planet's subtleties. Future sniffers will sample closer to suspected sources and climb through the air column to see how traces dilute with height. Orbiters will tune their lines of sight to emphasize near-surface paths at the right hours. Drills may reach down to icy layers where clathrates could lie, or to rock that remembers a warmer epoch in its pores. A single clean isotope ratio could weigh heavily. A cluster of organic fragments with consistent shapes could point even more firmly. The case will never rest on one reading. It will assemble by agreement among many. It helps that Mars is already mapped in other ways. We know where ancient deltas froze in place, where minerals formed in neutral water, where volcanic plains overlapped with basins that once held lakes. We can set a rover to drive from varved sediments to a fracture that releases seasonal brines, and wait for the air to speak. If methane is a messenger, we can put more listeners in the right rooms. There is tenderness in how this mystery sits. It neither promises nor scolds. It reminds us that worlds can keep small secrets near the surface for a very long time, and that the difference between something and nothing may be a few molecules per billion in the right breath of air. It asks for patience and for instruments that are calm enough to wait. Mars will keep the final word for now. We know enough to say the chemistry is possible, the geology is plausible, and the biology, if it exists at all, would be quiet. That is a complete thought to rest on, even if it is not an ending. The story is still being written at night, near the ground, where frost forms and lifts, and the wind remembers old channels in the dust. We leave the red plains without hurrying and turn to brightness. Around a golden planet, ice and dust arrange themselves into clean bands that catch the sun like new snow, then shed material into the gravity below. Their age is argued in measured tones, their beauty is not in doubt. Next, we listen to the rings of Saturn and ask how something so delicate can last so long, and whether it has. Saturn's rings look simple from far away, a pale band stitched around a golden world, gleaming where sunlight finds a billion turning facets. Up close they turn into a living texture, broad fields of ice and dust separate into lanes, lanes into ringlets, ringlets into wakes, and waves that rise and fade wherever gravity finds a rhythm. Everything moves, everything touches, everything adjusts. The puzzle is not why they shine, it is how long they have shone like this, and whether we are seeing them at a special hour in their long day. What the eye calls a ring is a sheet a few tens of meters thick in many places, and hundreds of thousands of kilometers across, a kind of planetary lake made of stones. Most of the mass rests in the bright A and B rings, with the dimmer C ring tucked inside. Beyond the A ring lies the narrow F ring, braided and restless. Closer to Saturn are the faint D and G rings, while far out the wide, diffuse E ring drifts like breath, fed by the plumes of Enceladus. Through the A ring, moons carve boundaries and corridors. In the Cassini division between A and B, a resonance with Mimas has cleaned a broad gap. Within the gaps, small shepherds patrol. Each feature is an echo of a particular pull, the way a harp string sings only when it meets the right touch. The particles themselves span sizes the imagination must walk through slowly. Powder-fine grains that act like smoke, pebbles, snowballs, ice blocks large enough to cast brief shadows as they turn. When two meet, they do not simply merge or shatter, they exchange momentum, shed heat, and separate with a fraction of their former speed. Those inelastic collisions create an effective viscosity. The ring behaves like a fluid because its constituents are small enough and numerous enough to share out energy and angular momentum by constant gentle impacts. Seen edge on, the sheet is thin. Seen from above, it is richly structured by its own self-gravity. Clumps gather into elongated streaks called self-gravity wakes, aligned with the direction of motion like brushstrokes laid by a very steady hand. Small moons are sculptors here, Pan nestled in the Enki Gap, and Daphnis in the narrow Aquila Gap, push aside nearby grains and raise waves whose crests curl along the gap edges. Prometheus and Pandora worry the F-ring from either side, tugging strands into braids and kinks that relax and then return, as though the ring were remembering an earlier shape. Even unseen masses reveal themselves by the signatures they leave. Miniature propeller-shaped disturbances mark where moonlets too small and dark to image directly plough lanes through the sea of ice. Everywhere in the bright rings, structure is the language by which gravity speaks. Yet it is the brightness, more than the grammar, that opens the quiet debate. Water ice should darken under the steady drizzle of micrometeoroids over very long times. Dust and grit settle onto the ring surfaces, tinting them with every tiny collision, and the collisions among ring particles themselves grind fresh surfaces that later take on the same stain. If the rain from space has been roughly steady for billions of years, the rings should look older than they do. Their reflectivity suggests youth or renewal, or both. A second measure adds weight to the feeling. When a spacecraft threads the gap between the rings and Saturn's cloud tops, the rings tug on it with their small gravity. That pull can be read as mass. The totals point to a system that is surprisingly light compared with earlier hopes. Light rings are easier to stain, easier to grind down, easier to drain. During those close passes, instruments also counted tiny grains and charged particles falling along Saturn's magnetic field lines, the so-called ring rain that carries water and nanograins into the planet's upper atmosphere. If that rain has flowed at today's measured rates for long spans, portions of the rings cannot long endure. In such a ledger, a lifetime of tens to hundreds of millions of years is not implausible. On the scale of planets, that is close to now. If the rings are indeed young, what made them? One picture imagines a moon nudged inward by resonances, until it crossed the planet's Roche limit, where tides tear apart aggregates that lack sufficient strength. In a slow catastrophe, the body stretched, split, and streamed into orbiting rubble. That rubble then ground itself to a finer distribution and spread into the bright fields we can see. Another picture conjures a large icy comet, or a captured body disrupted near Saturn, seeds for rings that subsequently evolved. There are variants. Perhaps an ice-rich moon lost its crust and mantle to tides and kept a rocky core that fell, leaving an icy ring as a kind of husk. Each version is careful with mechanics and materials. None requires anything outside the ordinary grammar of the solar system. The case for age is quieter but not absent. Rings can clean themselves in part, or at least appear to. The smallest dust is lofted by charging and radiation pressure, swept inward along the planet's field lines, or sputtered away by plasma, leaving larger, brighter pieces to dominate the light. Collisions can preferentially fling fine, darkened grains toward regions that diffuse them more quickly than they accumulate. Ballistic transport can move material radially as micrometeoroid impacts eject fragments that later rejoin the sheet at new distances. If such processes continually sort and recycle, a comparatively ancient ring could hold a surface that stays bright longer than a simple staining model predicts. There is also hidden mass to consider. The most opaque parts of the B ring are difficult to weigh because light does not pass through them easily. Dense tangle may conceal more material than remote measurements can easily see. If the total mass is higher than early estimates, lifetimes lengthen and resilience increases. Models grow less certain here because a ring made of many colliding pieces does not behave like a neat disk. Crowding can stiffen local regions and change how the pack transmits stress. The way a pile of ice flows resists motion until a threshold is crossed, then slips in a rush. Time's handwriting appears in waves. Spiral density waves propagate across the rings, where orbital frequencies match steady tugs from moons. Their wavelengths and amplitudes encode the ring's mass distribution and viscous response. Vertical corrugations, a faint up and down ripple, are likely the wound-up trace of a single, gentle tilt event long ago. As the ring orbits, differential nodal precession winds that initial nudge into a tighter and tighter spiral. Reading the spacing of those corrugations is like counting the rings of a tree to date a frost. Spokes, ephemeral radial shadows, seen at certain seasons, point to interactions between tiny charged grains and Saturn's magnetic environment, even to the way sunlight charges particles differently across the ring plane through the planet's long year. Seasons matter. When Earth's orbit carries us to a vantage where the rings are edge-on, they nearly vanish, a thin line stitched across Saturn's face. At other times, their full broadside washes the sky with light. The ring plane's tilt to the sun changes how shadows fall, how surfaces charge, how plasma interacts with grains. Processes that dominate one season fade in another. A single snapshot can mislead. Multi-year watching is necessary to hear the whole piece. The darkening rain from space is not constant either. The solar system's dust environment has its own history, its own cycles. Periods of higher infall leave more stain. Calmer eras give sorting and renewing processes time to polish. The inner system, anchored by Jupiter and Saturn and their gravity wells, acts as a sieve and a source. Even small changes matter when the clock runs this slowly. A ring that survives for hundreds of millions of years sees many such cycles and may look young during some and older during others. Beyond physics, there is the biography of the neighbourhood. Enceladus exhales through fractures at its south pole, building the E-ring with particles of water, ice and salt, and seeding the inner system with material that evolves under sunlight and plasma. While that outgassing does not resurface the massive A and B rings, the exchange of grains and charge fills Saturn's magnetosphere with currents and fields that touch everything nearby. Tethys and Dione hold tenuous, patchy exospheres. Mimas whispers gravity into the Cassini division. Janus and Epimetheus, two small co-orbital moons, trade positions every few years, slightly shifting the pattern of resonances and the waves they drive. Each small story feeds the larger one. The rings are not a separate entity. They are the middle chapters of Saturn's system written in ice. Open questions collect like frost in the shade. If a moon once crossed the Roche limit and fell apart, what signs would remain in the ring composition? Would we find an excess of certain salts or rock fragments in specific lanes, a chemical fingerprint of the mother body? Where did any surviving rock go? Did it fall swiftly, or mix, or reassemble into inner moons that now wear an icy veneer? If instead a captured body supplied the material, how often can such captures occur in a system like this? And what else would we expect to see as a result? On the other side of time, how exactly do the rings end? Do they thin to a ghost? Do they clump into arcs and then into new moons? Or do they rain away so steadily that nothing obvious remains but a memory in the planet's upper air? The answers sit in gentle differences among similar pictures, which is why this mystery is soothing to hold. One scenario is not a bright flare against the others. It is a slightly different shading. We weigh, we map, we watch through a long year and across a handful of solar cycles. Instruments measure micrometeoroid flux to tighten the stain rate. Radio and stellar occultations probe density where eyes cannot go. Thermal cameras read how quickly regions warm and cool, a clue to particle sizes and porosity. Over and over, waves are used as rulers. With time, uncertainties shrink, and models that once walked side by side begin to part. There are new subtleties that keep curiosity awake without spiking the pulse. Collisions, in a dilute, charged environment, do not mimic billiard balls. Grains charge, discharge, and polarize. Tiny lifting forces can grant a particle extra time off the ring plane before it settles back. In some regions, the mean free path between collisions grows so large that particles behave more like solitary satellites than like members of a dense pack. In others, crowding builds a kind of temporary stiffness that resists local shear. The ring is at once a fluid and a field of discrete bodies, a duality our language handles only by analogy. The better we measure, the more the duality feels natural. Imagining a young ring encourages us to think in chapters. Perhaps there was a time before when no bright shelf encircled Saturn. A disruption event begins the current episode. The opening scene is rough, blocks and fragments grinding, clouds of shards moving in and out of resonance, until enough energy is lost that the system flattens. The next scene's calm. Gaps sharpen, shepherds carve, wakes settle into their aligned streaks. Micrometeoroids start their work, plasma starts its work. Spokes flicker at certain seasons. A slow epilogue follows, in which the poem thins line by line until most of the ink sinks into the page. Even in that ending, there would be births. Small moonlets where mass clumps, thin arcs that drift and merge. The ring teaches how destruction and assembly braid. Imagining an older ring challenges us to respect equilibrium. Perhaps the destruction of icy bodies near Saturn is not rare on long timescales, and the ring we see is the visible face of a steady state, where additions and losses balance closely over ages. In such a picture, the brightness remains because supply, sorting, and removal maintain a running polish. The ring is not a transient fresco, but an ongoing workshop whose final product is never finished, only revised. Both ways of thinking have merit. The difference between them is a small bend in a line, not a cliff. Why does this question help a listener drift? Because the uncertainty has shape. There are no jagged stakes here, no alarms, only careful accounting of mass and light, only tides and collisions, and the whisper of charged grains along invisible field lines. The mind can walk among these processes without tripping. It can picture a moon torn into a ribbon, and that ribbon combed into bands. It can picture a thin rain of dust falling for ages, and a living ring that knows how to sweep itself clean. What arrives after the carefulness is the character of Saturn's realm. It is a place where gravity is not a single force but 1,000 small agreements, where orbits talk to one another, where a moon 100,000 kilometers away writes a wave on the ice in front of you. It is a place where a particle can be both stone and instrument, both a thing and a measurement. It is a place where time itself becomes visible as spacing between crests. The rings, whether young or elder, are the most legible diary of a planet we possess. Page after page they record resonances as lines, disturbances as spirals, seasons as changing gloss. Turning those pages slowly is what science does best when it refuses to hurry. There is a promise here that does not need words. Give us time, and the faint differences will sort themselves into a story that feels inevitable. We step away from the ring plane and look outward and inward at once. The rings are not isolated ornaments, they are consequences of large emotions. In the youth of the solar system, the giant planets likely wandered from their cradles, trading places with resonances, scattering and sweeping vast reservoirs of ice and rock. That migration would have rearranged the neighbourhoods, set the stages for later disruptions, and written rules that the rings still obey. And so we widen the frame. In the next chapter, we follow the giants through their early steps, patient and profound. We watch how a few slow shifts in orbit can rewrite a system, move lines of snow and stone, and seed the conditions for the worlds we see today. The dance is older than the rings and deeper than the gaps. Reading it brings the whole architecture into view. In the beginning, our system did not sit still. The giant planets felt the slow push and pull of the material around them. Gas at first, then swarms of ice and stone, and their orbits shifted the way a shoreline moves under a long tide. Jupiter, Saturn, Uranus, and Neptune are where we find them now, but the clues they left in smaller bodies suggest they once walked to those seats. One family of models, built from careful simulations, shows what happens when Neptune migrates outward through a disk of icy planetesimals. Each encounter with a small body trades a little momentum. One after another, the trades add up, and Neptune steps outward while the disk thins. The outward step shakes the Kuiper belt into the shape we see, populations locked in resonance, like the 3x2 Plutinos, a division between colder, low-inclination orbits and hotter, more tilted ones, a sparse scattering of distant objects on stretched ellipses. Along the way, Jupiter and Saturn brush past a key resonance with each other, and the whole system rephases. Trojan swarms brighten with captures, irregular moons appear around the giants, relics of a jumbled era that ended in a calmer arrangement. Another family of models rewinds further, to the years when gas still filled the sun's nursery. In those denser conditions, disk torques can pull a giant planet inward. Jupiter, in this picture, drifted toward the inner system until Saturn grew large enough to join the dance. Locked together by gravity, the pair reversed, turning back outward and tacking like a boat that has reached its limit in shallow water. The inward leg trims the building zone of the rocky planets, explaining why Mars is small. The outward leg stirs the asteroid belt, mixing dry, sunward rubble with darker, water-richer bodies from beyond. The inner system we know, small Mars, blended belt, emerges as a consequence of that detour. Both stories are grounded in the same mechanics: gravity trades, gentle drags, and timing. Both can reproduce many features of today's small body architecture. Neither is finished in detail. The moments of greatest uncertainty are the ones that keep curiosity awake without raising the pulse. Was Neptune's path smooth or punctuated by jumps? Did the resonance crossing between Jupiter and Saturn happen early, while gas still lingered, or later, after the small bodies had cooled into a fragile disk? How massive was that disk? How far did it extend? And did an extra ice giant, now gone, briefly join the lineup before being ejected into darkness? The small worlds act as our ledger, the wide range of inclinations among Jupiter's Trojan asteroids. the mixed taxonomic types in the main belt, the tight kernel of cold classical Kuiper belt objects near a particular distance, the presence of far detached bodies that Neptune cannot easily shape alone. Each pattern is a line of text. The more lines we read, the more we see that migration was likely not a single smooth stroll, but a walk with pauses, perhaps a stumble, perhaps a companion lost along the way. The giants do not tell their story directly. Their work is written into the orbits of everything else. Time scales matter, and they are gentle. Gas disks fade within a few million years. That is the window for the inward and outward tack. The sculpting of the outer small body disk can take far longer, tens to hundreds of millions of years, as each encounter carries only a slight push. Crater records once hinted at a sharp spike of impacts late in this period. Rereadings have softened that spike into a longer, slower tail, which fits a migration that winds down rather than ends abruptly. The system, in this view, relaxed into its present spacing, the way a stirred pond settles into ripples and then into sheen. There are intimate consequences. When the giants move, they sweep resonances across the inner system, shaking loose material that would otherwise have settled quietly. Some of that rubble falls inward, some outward. It is a way to deliver water and carbon to growing worlds that began too warm to keep their own supply. It is also a way to prune. Resonances can carve and clear as much as they mix. The asteroid belt's present diversity, the coexistence of bright anhydrous fragments and dark, volatile, rich ones, looks like the memory of a conveyor that reversed direction partway through its run. Not every clue is dynamical. Meteorites carry isotopic fingerprints. Comets and asteroids show different ratios of hydrogen to deuterium in their ices, different mixes of volatile compounds, different textures of organic matter. Earth's oceans do not match the simplest picture of delivery by only one class of bodies. A mixed origin, some water degassed from Earth's interior, some delivered from beyond the snowline in proportions that changed over time, fits better. If the giants wandered, they shaped the menu of what the inner worlds could taste. One of the quietest ideas is the possible fifth giant planet. In many simulations, an extra ice giant interacting with Jupiter provides exactly the size of kick that reproduces the spacing and eccentricities of the surviving four, while reducing the chance of wrecking the inner system. That extra world then leaves, ejected to interstellar space. Nothing in physics forbids such a departure. Stars and planets scatter bodies into darkness all the time. If it happened here, the only records would be the orbits that remain, and the populations that were captured in passing. We test these pictures by building them forward. Numerical experiments place millions of small test particles in a disk, let the giant planets migrate according to simple rules, and then compare the final distribution with what telescopes see. When the match is poor, too many high-inclination bodies, or too few resonant captures, we adjust the path and try again. The goal is not to force a single answer, it is to narrow the family of histories until the plausible ones share a shape. The constraint that matters most is serenity. The inner system must remain a place where Earth could form mostly undisturbed, yet be furnished with the materials it needed. There is comfort in the way the unsettled pieces fit inside clear bounds. We do not need to invent new forces, we need to tune the timing and the mass, and accept that migration is the default when large bodies sit in seas of smaller ones. A planet is not a fixed monument, it is a traveller whose route can be read after the journey ends. The reading takes longer than the trip, which is appropriate for a subject that moves in centuries and settles in eons. What we gain beyond specific answers is a sense of architecture. The solar system is not a set of isolated shelves. It is a house where one renovation changes the light in every room. When Jupiter and Saturn moved, they shifted the line where ices could condense. They rewrote the neighbourhoods where rocky worlds could gather. They pulled and pressed on reservoirs that later sent visitors inward. The quiet implication is that other planetary systems, now seen in their thousands, are likely just as changeable. Hot Jupiters skimming their stars, chains of sub-Neptunes in resonant steps, belts of debris offset by unseen shepherds, all look like the signatures of migration written in other architectures. In the absence of an eyewitness, we use what the system kept. Patterns in the Kuiper belt, the tilt and spread of Trojans, the mix of the main belt, the capture of distant, irregular satellites, whose distant paths speak of a chaotic time, the placid circularity of the giants' present orbits compared with the looseness of the small bodies left behind. Each is a postcard mailed from an earlier address. Two thoughts to close. First, the giants did not merely wander. They set the conditions for every ocean and atmosphere that could later appear. Their routes determined which reservoirs were tapped and which were left alone, which gradients were established and which erased. Second, the uncertainties that remain are narrow doors, not open fields. As surveys of the far belt deepen, and as models learn to carry more physics, the plausible histories converge. The story is already legible in outline. The final revisions are a matter of phrasing. Next, we turn to the blue question their journey helped pose: how a dry young Earth came to carry so much water. The answer is not a single delivery or a single breath from within, but a balance written over time. We will read that balance in isotopes, in rocks, and in the timing of the rains that could fall only after the light had softened. Picture the young Earth under a sky of steam, rock still soft from a global melt, air thick with water vapour and volcanic gases, sunlight caught and scattered by clouds that had not yet learned to rain. As the crust cooled, the first deluges fell and kept falling, water meeting basalt, carving the earliest basins, then boiling back to cloud and returning again. Between those cycles, an ocean took hold. Where did that water come from? Part of it rose from within. As the magma ocean froze, dissolved volatiles, water, carbon dioxide, sulfur species, exsolved and built a heavy wet atmosphere. With time and cooling, that vapour condensed to seas. Another part arrived from without. During and after planet building, small worlds from beyond the snowline, rich in hydrated minerals and ices, spiralled inward and shattered, delivering their stores. The blend of breath from stone and gifts from space is not a compromise, it's the shape of the truth. Chemistry keeps the score. The hydrogen in our oceans carries a fingerprint, the ratio of deuterium to hydrogen. Earth's seawater matches most closely the values in carbonaceous chondrite meteorites, ancient dark material from the colder reaches of the early disk, rather than the average for long-period comets. That does not forbid comets, it lowers their share. The match suggests that many couriers were asteroid-like bodies from just beyond the young Jupiter, nudged sunward during the giant's migration and ground into rain. Rocks add older notes to the ledger. Tiny zircons from ancient crust, some over 4.4 billion years old, contain oxygen signatures that form in the presence of liquid water. Whatever chaos followed Earth's assembly, surface water was present astonishingly early. Deeper down, minerals that trap hydroxyl within their lattices, like ringwoodites sampled in diamonds from the mantle, hint at a hidden reservoir, vast not as free ocean but as bound water inside rock. That deep store joins the cycle slowly, rising in magmas and returning to depth in slabs. A planetary lung that breathes on geologic timescales. There are counterweights. The giant impact that formed the moon likely stripped and vaporized a portion of Earth's early volatiles. Solar ultraviolet light split water in the upper air. The light hydrogen fled to space. These losses pressed the system toward dryness, yet delivery and degassing pushed back. The result is the ocean we know. Not a single inheritance, but a balance that continued to adjust for hundreds of millions of years. Even the dry rocks can wet themselves. Where fresh ultramafic rocks meet warm water, hydrogen is set free. Carbon dioxide and hydrogen then form methane and other simple organics in a suite of reactions that feed chemistry favourable to life. That alchemy, serpentinization, works without sunlight and suggests that the first useful gradients for life could have been as much about geology as about rain. What remains unsettled is timing and proportion. How much water was present before the moon-forming impact? How much came with the late veneer of small bodies afterward? How much has cycled in and out of the mantle since? Nitrogen and noble gas isotopes sharpen those questions without closing them. They point to mixtures, not single sources. Models of accretion now include pebbles and dust that carried adsorbed water inward on drifting spirals, quiet trickles that add up when the clock is long. The comfort in this puzzle is its restraint. There is no single dramatic answer to chase, only a clear, accumulating picture that our ocean is the sum of calm processes, degassing, delivery, cycling, working together across deep time. The early planet learned to keep water the way a hearth learns to hold heat, not all at once, but by patient adjustments in stone, air, and light. Earth's blue skin did not appear in isolation. It formed under a star whose wind and light can strip or spare an atmosphere, inside a magnetic cocoon that changes the rate at which gases escape. To understand why the water stayed, we step to the boundary of that cocoon, where the solar wind meets the interstellar medium, and read the shape of our sun's invisible shore. Out beyond the last bright planets, the sun keeps a wind. It is not air, but a stream of charged particles and tangled magnetic fields spilling outward in all directions. A river of plasma that starts hot and fast near the solar surface and coasts into the dark. For billions of kilometers, that wind runs supersonic. Then, far from home, it meets the thin gas between the stars. The wind slows, heats, and thickens. It forms a sheath and a boundary. It gives way to the galaxy. That borderland is our Heliosphere's shore. Names sketch the map. Where the solar wind first breaks to subsonic speed is the termination shock. Beyond it lies the heliosheath, a turbulent buffer where solar and interstellar plasmas mingle and trade energy. Farther still is the heliopause, the contact where the sun's influence yields and the interstellar medium takes over. Outside, the local galactic environment flows past, carrying its own magnetic field, its own neutral atoms. If the sun's motion through that medium were fast enough, and the conditions right, there could be a true bow shock ahead. Current evidence favours a gentler bow wave, a compressed but not shocked region upstream. For decades this was only a diagram. Then two elderly spacecraft, launched in the 1970s, drifted outward for half a human lifetime and entered the map. One crossed the termination shock, and years later, the heliopause, suddenly hearing galactic plasma vibrations loud and clear. The other, in a different direction, felt the same steps at different distances. The crossings were not neat. The boundaries moved with the solar cycle, breathing in and out by billions of kilometers, layered like gauze folded by magnetic drapery. Still the message held: the shore exists, and it is a place, not a guess. Even so, shape is the question that keeps its mystery. For a long time, we imagined a comet-like heliosphere, blunt in front and trailing a single tapering tail downstream. It is an easy picture to hold. A wind meets a flow, the structure elongates, but the matter is subtler because the heliosphere is not a solid body leaning into air. It is a pressure balance among moving plasmas, magnetic fields, and a surprising population of pickup ions, neutral atoms that wander in from the galaxy, become ionized within the heliosphere, and are then swept up by the solar wind, carrying most of its energy in the outer regions. Those pickup ions change the rules. They make the heliosheath hotter and thicker than simple models expected. They blunt the nose, they soften the tail. Another competing picture grew from global images of the boundary. We cannot photograph the heliosphere directly in visible light, but we can infer its global outline using energetic neutral atoms. When a fast ion in the heliosheath grabs an electron from a cold neutral atom, it becomes neutral and flies off in a straight line. Map those neutrals across the sky, and you draw a portrait of the pressure and turbulence out there. The maps showed surprises: a bright ribbon aligned with the interstellar magnetic field draped over the heliosphere, and hints that the downwind region is not a long streamer, but a pair of lobes. In this view, the heliosphere looks more like a rounded croissant, with two magnetically collimated jets downstream. Magnetic tension from the sun's wound-up field pinches the flow, separates it into twin outflows, and leaves the sides fat rather than stretched. Which is it? The cautious answer is neither simple caricature, and both, in part. The heliosphere is likely blunt up front, because pickup ions carry the pressure there. Downstream it may separate into two extended lobes rather than a single tail, because the solar magnetic field's tension and the interstellar field's draping guide the escape. The detailed form changes with energy. Lower energy neutrals trace one outline. Higher energy neutrals trace another. Over the 11-year solar cycle, the solar wind's fast and slow streams trade dominance, and the whole boundary shifts its posture. The interstellar medium contributes its own handwriting. We are moving through a puff of warm, partially ionized gas with a particular flow speed and magnetic field direction. Those vectors matter. They set the angle at which galactic field lines wrap around the heliosphere, and thus where pressure piles up and where it eases. In some models, the field lines slip around the heliosphere like water around a rounded stone. In others, they grab and tug, creating folds and cuffs. Switch the interstellar conditions, and the same star could wear a different shape. Closer in, the heliosheath is a workshop in small processes. Charge exchange between hot ions and cold neutrals creates a constant swapping of identities. Instabilities wrinkle the current sheets where magnetic polarity flips. Turbulence turns ordered flows into swirls and eddies. Those eddies feed back on the large-scale pressure and change the thickness of layers. The pickup ions, born from neutral gas wandering in from outside, behave as a warm reservoir that cushions the solar wind's deceleration. All of this matters for shape, but it also matters for what the heliosphere does. It modulates cosmic rays, the high-energy particles that arrive from supernovae and other distant engines. In quiet years, the heliosphere's magnetic fields and waves are better at deflecting and slowing those intruders. In active years, the gate is looser. The modulation is not a wall so much as a weather pattern, and Earth lives under its changing sky. Our best images of the global edge come from steady, patient mapping of energetic neutrals. Over time, those all-sky portraits change, brightening along the magnetic ribbon or dimming where pressure drops. Their cadence is slow. Sometimes years pass before a new pattern emerges. Alongside them, the old Voyagers continue to sample directly, measuring plasma densities, magnetic field strengths, and the rain of galactic particles on either side of the heliopause. Their lines of sight are narrow, their readings are local, but they anchor the global maps with truth on the spot. If the shore has a lesson, it is that boundaries in space are not lines, but regions. The termination shock is not a crisp frontier, it is a messy change from one kind of flow to another, spread over distance by turbulence and charge exchange. The heliopause is not a hard shell. It is a place where magnetic fields thread through and sometimes reconnect, letting a little of inside mix with a little of outside. Even the notion of inside is gentle. Neutrals pass in both directions largely unhindered. Ions and fields do the negotiating. The unsettled pieces remain graceful, exactly how thick the heliosheath is in different directions. Whether the downwind region is truly bifurcated or simply broken into knots that look like lobes when averaged, how the ribbon forms in detail, whether it is a line of sight effect where we look perpendicular to the draped interstellar field, or a genuine pressure enhancement where pickup ions linger. Each of these is a small turn of emphasis among pictures that already share most of their outlines. No new physics is required, only more careful accounting of known processes and better time coverage. Why this mystery rests well in the mind. because it is a shield that works without drama. The heliosphere does not blaze, it balances. It keeps most of the galaxy's charged particles at bay, not by stopping them cold, but by meandering their paths and bleeding their energy. It breathes with the sun. It trades with the neighbourhood. It reminds us that even on the scale of light years, softness and patience change outcomes. In time, the portrait will sharpen. A new generation of sky maps will trace energetic neutrals at more energies and finer resolution, stitching a time-lapse of the boundary seasons. The Voyagers will keep sending their quiet numbers until their power fades. If a mission someday flies a dedicated probe outward with modern instruments, it will sound the layers like a careful diver. Modelers will fold pickup ions into their simulations from the start instead of treating them as a footnote. Each step will favour one contour over another until one description feels inevitable. For now, the shape of our shield is best held as a family of possibilities. Blunt in front, wide at the waist, downwind not a single tail, but a parted flow. A boundary that breathes, a shield that filters rather than blocks. The poetry here is not metaphor, but balance among pressures, fields, and particles that are real, countable, and kind. And here is the quiet gain from knowing any of it at all. When you look up, the sky is not only stars. There is also a slow bubble around everything you have ever known. A moving room whose walls are made of plasma and magnetism, whose doors open and close with the sun's mood. To learn its shape is to trace the edge of home. Tonight we traced quiet riddles close to home. A thin visitor slipping through the dark, a possible shepherd at the edge, oceans turning beneath ice, a planet that chose to lie on its side, a veiled twin warming under cloud, a red world's shy breath, rings that shine like snowlight, giants that once drifted, blue water gathered and kept, and the sun's soft border with the galaxy. Each mystery stayed gentle in the mind, clear in outline, calm in tone. Let the questions loosen now. Let breath fall in and out, easy and unforced. Let shoulders drop. Let the room grow wider and quieter. The sky will keep these puzzles until morning. They do not need you to hold them. You did enough for today. Close the door of thought, float a little, and rest. Good night, Voyager.